Welcome again. This is Dr. Ali Mugabil and we're doing random processes. In the current lecture we'll look at the joint distribution, independence, and we'll look at moments. All of this is for random processes. We have seen this for random variables and it's time to look at random processes. The distribution and density function. Recall that in the diagram shown on the right hand side here, you can see that taking any instant of time define a random variable. A random variable is defined by a CDF or the PDF. So you can define every instant of time by the PDF probability density function or by the CDF, the cumulative distribution function. Now a random process is more than that. So we need a PDF and a CDF for every instant of time. We also need to have the joint relation between them. So a random variable here is characterized, by a PDF or CDF. How do we characterize a random process? We just mentioned to fully define a random process, we need n-dimensional, where n represents the number of time instances, n-dimensional joint density function, not just individual density function. We need the joint to keep the relation in time. That's really complicated, but don't worry, we'll try to make things simple. So just formally we'll define them and then we'll see how to go or to get away from defining CDF and PDF. A joint CDF and PDF with n dimension. First, if we define the distribution function, so capital F, and we have x1 here, semi-comma t1, it is the probability that x at t1 for a given time is less than or equal to x1. Now if we incorporate two time instances, we go into the second order joint distribution function, where a given instant of time is less than a given value, another instant of time is less than another value. So basically we here consider two time instances and their relation. We call it joint second order. You can go as much as you want. We can until the nth order, which include all the time instances. So we have the nth order joint distribution function, and of course the PDF is related to that by the partial differentiation because we have multiple variables now. Note the notation here. We have x1, x2. These are the values of the CDF, and then we have semi-comma. And then we list the time instances. We have T1 up to capital Tn. As I just mentioned, the PDF and CDF are related by integration differentiation. And if we have multiple variables, then we'll need partial differentiation. We can also extend the concept of moment from random variable to random processes. We have two types here. We have correlation and then we have covariance, right? But even then, we have two subdivisions. One will be called the O2, and the other would be cross. So let's take it easy. Let's start by the mean, the first moment. The mean of a random variable x now, we used to call it m sub x. Now it's function of time. The new thing here is that we have explicit function of time because it's a random process, and we get the expectation of the random process. The answer now could still be function of time. It does not have to be a constant number like 5, 6 or so. It could be like t plus 1. It's a function of time in general. That's the mean. Let's go to the correlation. We have two types again. O2 correlation. The word O2 is used when we are looking at the variable with itself. So it's the expected value of x1 times x2. Now we are showing the relation with time. Again, we have rxx. We use r for the correlation. If it is autocorrelation, it would be from x to x itself, from the variable to itself at two different instances of time. Again, we are extending the definition. So you take the random variables, x1, x2 multiplied by the joint PDF and the joint PDF for the random process, and then you integrate. We can also define the auto covariance where we subtract the mean. Once more, the mean is still a function of time. Exactly like we did before, it's just extension. This is called autocorrelation and autocovariance. And we can still maintain the relation between CXX and RXX, the covariance equal to the correlation minus the multiplication of the means at two different instances of time. We can define the cross correlation. Cross, whenever we have cross, it means we have two different variables. We have X and Y. The cross correlation now is defined, the autocorrelation between two different random variables. We have now the cross correlation. We have X and Y measured at different instances of time. We look at the expectation of the product and we call it the cross correlation. Similarly, we can define the cross covariance, where we subtract the mean. And we also can find the relation between the cross covariance. Notice that in cross, the subscript are different. We don't have XX or YY, we have XY. That's equal to the cross correlation minus the multiplication of the means. We had similar equations before, but we are extending them now to random processes. For the case of independence and correlation, we can define two random processes. We can declare two random processes to be independent if the joint PDF equal to the multiplication of the marginal PDFs. Like if you have two variables, X and Y, and you are observing them versus time, weight and height, and they are also incorporating different times, then the joint PDF is going to be, if they are independent, it's going to be the product of the marginal PDFs. I'm just distinguishing here things with color so that you can tell that we have Y in red and the associated time variables is also in red. So we need different time variables for X and Y. We're not just comparing them at the same instant. We're comparing the weight now with the height after 1 year and so on and so forth. Okay. If X and Y are uncorrelated, then the covariance equal to 0. If X and Y are orthogonal, the correlation equal to 0. And if they are independent, we can conclude they are uncorrelated automatically. So now we move into stationary random processes. When do we call a process to be stationary? Just the word stationary means something that does not move. So stationary random process, if all statistical properties do not change with time, okay, we get things to be stationary. Because it's random, we don't expect everything to be fixed with time. So we define different levels of stationarity. We have first order stationary process. A first order stationary process, if the PDF at a given instant of time is not changing, which means we can do the test now or tomorrow. If we are interested in a specific instant of time, things are stationary. So adding delta t to the time variable does not change the fact. And of course, if the PDF does not change with time, you expect the mean or the expected value of the random process to be constant because it's not a function of time. We can prove this quickly. Okay, if this is true, if the PDF does not change by one time shift, by delta shift, then we can define two random variables at two instances of time, x1 and x2. So we do have different random variables. If you take the expectation of these two random variables, because you want to find the expectation, then it's multiplying by x, and then we have two different instances of time. We can define t2, the second time, to be t1 plus delta, because any function, any time can be related to the other one with a shift of delta. So now we can write the expected value of x of 2. I'm just replacing the time variable here. It becomes t1 plus delta. Now, if they don't change, if it is constant, then of course you also expect that the mean will not change, like we are concluding here. In fact, it's very obvious, because if the PDF itself is not changing with time, expected value is just a first moment of this PDF, so it should not change. Now, we can also define the stationarity on the second order. For the second order stationarity, or we say stationary to order 2, the PDF evaluated, the joint PDF evaluated at two different instances of time, still maintain its relation, even if you shift with delta t. Remember that this shift in delta t, this joint PDF, it means that at T1 we have the same things at T2, and also the joint relation, the spacing. So if you are interested in how much your weight changes within 1 month, so, and it's stationary, you can take January, February, or February and March, because it's a second order stationary, assuming. So 2 different instants of time can be shifted without a problem. So we can also prove this by letting delta equal to minus t. Then, of course, if you substitute here delta with minus t1, okay, and similarly here we get minus t1. So now this first term becomes 0, second term becomes t2 minus t1. So in fact, it's just a shift in time. We can make the following statements. A second order stationarity guarantees first order stationarity. Okay, a second order stationarity guarantees first order stationarity, because we can look at the PDF, the marginal, you can think of this as a marginal PDF. By eliminating x2, you integrate from minus infinity to infinity. Okay, and then because it's a second order PDF, we can go from here to here by replacing time with delta. Okay, and then this is nothing but, if you look at this, the first part, it's nothing but the PDF of T1 plus delta. And because it is this guarantees you it's a marginally, if it's second order, it's going to be first order stationary. Now a second order stationarity, or we can write it this way, for example, it's a T1 plus T plus tau, any time shift. We can write T1 and T2, or we can use the T1 and T2, or T1 and T1 plus tau. If it is second order stationary, of course you expect the correlation to be function of time difference only, because the correlation function is a second order moment, and if it's stationary, then all we need is just delta. That's a very important statement. So correlation does not change with the time, it just changes with tau, the time difference, where tau equal to T2 minus T1. So we can summarize this level of being stationary. We have different levels. We call it wide sense stationary, WSS, wide sense stationary, if the mean is constant and the correlation is function of time difference. It's not function of t. There is no t here, so it's not function of time. We call it a second order stationary, which is a higher level, if it is wide sense. I mean, if the PDF, the joint PDF, does not change, okay, with 2 time instances. Of course, second order stationarity guarantees wide sense stationary. It's something bigger, okay, but not the reverse. Now, an nth order stationary assumes that the PDF up to the n order does not change with a time shift. Of course, nth order stationarity guarantees less than that order of stationarity. So if n equal to 5, of course, if we have k equal to 4, for example, you can tell that it guarantees to be fourth order stationary. But if I say it's strict sense stationary, or stationary in the strict sense, it means that's hard-minded stationary. It means everything is not changing with time. The PDF remains the same. So that's the worst type. So joint, we can also define joint wide sense stationary for 2 random variables. We can think of this as their cross correlation is only a function of time difference. Of course, they have to be wide sense stationary. Now, we can think of this following circles. It's going to summarize things. We have the strict sense stationary, which is the biggest circle. It guarantees everything inside. So if it's strict, it's automatically second order. And if it's second order, it's automatically wide sense stationary. And if it's wide sense stationary, of course, it's first order stationary. Now, we can look at wide sense stationary example. It says, show that the given random process defined to be the following, all right, is a wide sense stationary if it is assumed that A and omega naught are constants, and theta is uniformly distributed random variable on this interval between 0 and 2 pi. So he wants us to prove that it's White stationary, which means we need to find the mean and prove that it's constant, and then find the correlation. Remember that we can write it in another way here. This is the function we have. A and omega naught are just constant, so what changes is only phi. Remember that phi is uniform distribution between 0 and 2 pi, 0 and 2 pi, which means the amplitude of this, to keep the area equal to 1, it's uniform, so it's constant, must be 1 over 2 pi. So the area or the PDF of phi is equal to 1 over 2 pi. This use is just to indicate the starting and the end points. Okay, so if somebody wants to find the expected value of x of t, of the cosine, then I'm going to scale the PDF. I'm going to scale the function. Here is the function, here is g of t. Okay, this is g of t, or g of phi, multiplied by the PDF of phi, and then you integrate over the limits from 0 to 2 pi, because it's only 1 over 2 pi in this limit. And you will find out that this is going to give you 0. In fact, the average of a cosine over 2 pi is always going to give you 0, no matter what the shift is. You have a cosine, full cosine, or minus cosine. Okay, it's going also to give you 0 if you average out the area under the curve. So the first condition is met. It's constant. It's even 0, not just constant. It could be 5 or 3, it's still fine. Now the second thing we need to prove is to show the correlation. By definition, the correlation is the expected value of the function multiplied by a shifted version of that. So here is the function. I got a squared outside because a is just constant. So I'm substituting here. In the second item, I'm shifting the time by t plus tau. So we have t, which is the original time, shifted by tau. So let's open the bracket, solve things out. Our objective is to see, do we still get the time variable, or does it disappear? If it disappears, then mission accomplished. If not, then it's not stationary. So cosine times cosine, we use our trigonometric background. It's equal to half. Cosine the sum, cosine the difference. So to go from here to here, we're using geometry, we're using trigonometry, and then we're using our background. So it's going to be half times expected value of cosine sum, cosine the difference. Okay, now what is the expected value of cosine? We just have seen this before. If you take the expectation, which you mean you're going to multiply by the d, just like we did here, then you're going to get 0. Why? Because we are integrating cosine over full 2 periods, in fact, because we have doubled the frequency. But 1 period or 2 periods is going to give you always 0, no matter what the phase is. So you can do it by inspection, or you can take the long path and then do the substitution yourself and get something similar to what we have here. Okay, now this term is going to disappear, and what remains is the first term, half cosine omega naught tau. Now clearly that this term does not have t, it's not function of time. So we can conclude that this is an example of White stationary because the two conditions are met. Constant mean and autocorrelation doesn't have to be constant. It just does not have to be function of time. It still can be function of tau. Here's a practice problem. I will leave you with this practice problem. So please, you can answer this question in the comment section. Consider a random variable, a random process, which is given by 3t plus b, where b is a uniform distributed random variable in the range from -t to t. Determine the mean and the autocorrelation of x of t. Is it White stationary? And we'd like you to justify your answer. Okay, so I think clearly we can find the mean here. I'll leave you with the rest. The mean is the expected value of x of t, which equals to the expected value of 3t plus b. Okay, so now what's the expected value of b? Okay, it's a random variable. It's uniform distributed between -2 and 2. We can tell clearly it's 0. So it's going to be the expected 3t, which is not time is not a random variable, so it's going outside 3t plus the expected value of b, which is equal to 3t. Now we can immediately conclude that this is not going to be White's stationary because the mean itself is not a function of time. It changes with time. So you would love that our weight is not function of time, because otherwise if it has a positive time, if you assume that your weight is a random process and you don't want to see the time multiplied by a positive quantity, because this means that your weight is going to increase with time, which is not something that you usually want. Okay, I leave you with the autocorrelation, the expected value of x of t times x of t plus tau, and then of course share your answer please in the comment section. Thank you.